So this is the section 7.3 lesson video. Okay, so we've already covered 7.1, 7.2 in class, and so this is the last kind of little snippet of 7. And it's really easy, really short. If you're looking at your notes packet right now, you'll see that, it's not very long and it's pretty easy, so that's why, again, we're doing it as a video lesson. Alright, so 7.3 kind of touches on bonding in metals, because the rest of 7 we've been talking about ionic bonds. Those are between a metal and a non-metal. When we get to chapter 8, we're going to talk about covalent bonds. Those are between only non-metals. So we do have to talk about metallic bonds a little bit, and so that's, of course, bonding that happens in metals. So the valence electrons of metal atoms can be modeled as a sea of electrons. So in normal circumstances, the electron stays with the nucleus it belongs to. So in like an ionic compound, whoop, that marker's no good. In an ionic compound, if we have a nucleus that's positive and we have a negative electron, it stays with this nucleus. Like if there's another nucleus over here, it doesn't go over there, it just stays with the nucleus it belongs to. Okay, now that's not saying like in ionic bonds we know that some are transferred, but of course once they're transferred, they stay with that nucleus. In metals, the valence electrons just go wherever they want. So like if you look at this picture right here and see the electrons moving. Let's say we have an electron that was originally over here. It can kind of hang out over here, it can come over here if it wants, it can jump on over here, jump down here. It can go wherever it wants. And so since those valence electrons can move and move around, that allows them to conduct electricity. Okay, so how does this happen? Well, metallic bonds, they're between the attraction of the free-floating electrons, which are the valence electrons that are moving around, and the positively charged metal ions. So these ions, they're positive, and those valence electrons just kind of travel around between the different metal ions. And again, metals are good conductors and they're malleable because of these mobile electrons. You need charges that can float in order to conduct electricity. So when you hook, if you were to hook this piece of metal up to, a circuit, then all the electrons would flow in the same path, and that would allow it to conduct electricity. All right, so let's talk a little more about metals. Now, as much as you might not think metals look like a crystal, metals are the most simple crystals because they contain one type of element. Now, again, lots of you want to think of crystals as, gemstones, diamonds, that type of thing. Those are crystals, but anything with a 3D repeating pattern is a crystal. So salt is a crystal, sugar is a crystal, ice is a crystal, and metals also have those 3D repeating patterns. We just don't normally see them in their crystal form. So if you look right here, you can actually see the facets of the crystal on this metal. Okay, normally we melt it and we want a nice smooth surface. We don't want it to crystallize. Okay, but metals can crystallize and actually look like crystals too. But remember, it doesn't have to look like a crystal to be a crystal. It has to have a 3D repeating pattern called that crystal lattice. Alright, so let's talk about alloys. So an alloy, as we talked about in chapter 2, is a mixture with metallic properties. There are 2 different types that we're going to talk about. That is a substitutional and an interstitial alloy. So a substitutional alloy is exactly what it sounds like. If I had a substitute, then I would not be here and the substitute would be here. So I would leave and the substitute would come in. And so that's what happens in a substitutional alloy. Let's say that we start with one type of metal, and then we introduce a second type. I'll just color those black. We introduce a second type of metal that's going to substitute. So this metal atom might leave and become the new metal. All right, this metal atom might leave and the new one might take its place. This one might leave, the new one will take its place. So forth and so on. So some of them are replaced. And so that is what it would look like. Now for substitutional alloys, the metal atoms tend to be of similar size in order to be able to replace each other. On the other hand, interstitial alloy, if you'll think of interstitial and remember the word insert. In an interstitial alloy, smaller metal atoms are inserted in between larger metal atoms. So what that means is, let's start with our metal again. So this is our metal, and we introduce a smaller metal atom. Because they're smaller, they can't really replace the larger ones, but they can fit in these little spaces in between. They insert themselves in between the larger metal atoms. Okay, and so this would be what interstitial would look like. Now, remember, on my tests, I like to do charts, lists, and pictures as my free response questions. So make sure you can draw these pictures. Okay, so substitutional metals of similar size are replacing one another, and in interstitial, metals of smaller size are inserting themselves in between the larger ones. All right, so let's look at that section assessment. I told you this section would work. So, how do chemists model the valence electrons in metal atoms? Well, remember, they're mobile. They can move around, they can flow, so they call them the sea of electrons. All right, it's the sea of electrons. That's how they model the electrons. Oh, I almost made it.
Good morning. I need the following teachers to please report to the large conference room at this time for a meeting. Scarano, Spalding, Schwartz, McCrory, Simpson, and Drain. That's Scarano, Spalding, Schwartz, McCrory, Simpson, and Drain. Please report to the large conference room at this time.
If only I knew how to edit videos, I could get rid of those interruptions. All right, so anyway, number 2, how do you describe the arrangement of atoms in metals? Well, of course, remember we said it's the sea of electrons. They can flow because they are mobile. They are mobile. They can move around. Oh my gosh, I'm just going to...
Good morning. We need the following teachers to go to room 517 for a meeting, please. Miss Lawrence, Mr. Parham, Miss Lisa Bullington, Coach McDonough, Miss Lomberg, Miss Campbell, Mr. Howard, Miss English, Miss Gibbons, Miss Stevenson. You're needed in 517 for a meeting, please. Lawrence, Parham, Lisa Bullington, McDonough, Lomberg, Campbell, Howard, English, Gibbons, and Stevenson.
All right, it's obviously announcements time, so let me hurry on the last 2. So why are alloys more useful than pure metals? Because we enhance the properties we want. Like stainless steel, we enhance the ability that it resists rusting. So we enhance the properties we want. Aluminum alloys are used a lot to make something lighter, less mass, or less heavy. Enhance the properties we want. All right, last one real quick before I get stopped again. What's meant by ductile and malleable? Ductile means can be pulled into wires. Malleable means can be hammered into sheets.
Mr. George, please return to the front office. Mr. George, please return to the front office.
Woo! This video had lots of interruptions. All right, so before I get stopped again, that was 7.3, ductile pulled into wire, malleable hammered into sheets. Sorry about all the intercom interruptions.